is going to be a small tutorial over the 8-point FFT and the 1024-point FFT, and we will be seeing how this Pynq workflow is different from the SDK workflow that we are working with. So let's just start by creating a new project. I will just name it FFT_8 and yeah, do not include, and in the boards I will be selecting the Pynq set to board and finish. So now let's start by creating a block design. Let's name the block design to FFT_8. And okay, so we will first add our PYNQ IP. We'll run the block automation, and after that let's enable the HV ports for now. I'm enabling HV0. Then we will add the DMA IP. Let us configure it. So we will disable the scatter gather engine. We will increase the buffer length register to 26 bits, and we will change the memory map width and the stream width to 64, and that should do it for the XIDMA itself. We will look into why this was changed to 26 bits and why we need to change the memory map width and the stream data width to 64. So once that is done, we can again run connection automation, and it should, yeah, so it should connect the EXI light and the HP0 ports on the Zinc and the DMA IP. So let's just regenerate the out once. We will reconfigure this once again, and yeah, so now you can see that the MEXI memory map to stream and stream to memory map ports are connected to a smart interconnect, which are connected to the HV ports, and we are connecting the AXE light via interconnect, AXI interconnect, to the GP ports here. So once this is done, let's just regenerate it, and now what we will do is add our FFT IP. So we will do FFT, we will click on this, and so in the FFT IP, okay, it is added here. Oops, let's bring it down here, regenerate it. Now we need to connect this FFT IP, so for that we will connect this memory map to streaming port to the SEXI data port, and we will connect the MEXI data port or AXI stream data port to the slave AXI stream to memory map port for the DMA. Let us also configure how the IP looks like. Yep, so we want to do a 8-point FFT, so I am changing the transform length to 8 points. In the implementation, I would be sending it a floating point value, so I need to change it from fixed point to fixed point to floating point. I would require a reset signal if I want to reset my IP, and after that I want my output ordering to be natural order. Once that is done, we can click OK, and it should configure my IP properly. And some things that we want to see is basically here the data is 63 or 64 bits, so we want to make the read ports or the write ports, the read and write ports to be 63 bits or 64 bits to send and receive the data, rather than 32 bits. So this once this is done, this would be automatically changed by the when the FFT IP is connected, it would be automatically changed, and this we need to configure by ourselves. So let us do a regenerate layout, and one thing we can do is we can create a hierarchy for now to make it a little bit more tighter. So basically I am keeping everything in a hierarchy which is not directly connected to the processing system. So we can keep any of the IPs or any of the interconnects in the hierarchy, but the idea is we want to keep the interconnects outside the hierarchy, so we can see what all signals are needed by that signal. So we will control click on both of them, we will right click, and we will create an IP. Let us name the hierarchy to be FFT_block. So once this is done, we can regenerate the layout, and now our design looks a little bit simpler, a little bit tidier, and we can see that the FFT block is using two master ports which are streamed to memory map and memory map to stream to communicate to the processing system, and it is also using one of the GP ports using the AXI interconnect to configure the DMA, and which is your SAXI light port. So if I want to change anything inside the hierarchy, I can just double click and it will show me how the internal hierarchy looks like. In the internal hierarchy, you can see all the signals which are sent and received inside the IP or inside the hierarchy and sent outside the hierarchy are made internal and external. For example, here this SAXI light is mapped as external, and also these two MEXI memory map to stream and MEXI stream to memory map are also external. Similarly, the clocks and the resets are also external. So at this point, let us just connect the clock and reset. So first of all, let's add the clock and reset to the specific clock and reset. So here they are connected, and now let's look how this SAXI config should be configured. So we want to send some data to the or some configuration to the FFT IP of how it should behave. So for that we will just give it a constant value. So here we can take this constant and connect it directly to the T valid signal, which is an input, and the value of this is 1. So the constant value it is driven to is 1, and the width of the constant signal is also 1. So the T valid signal is a 1-bit signal, so we will give it a 1 always. And for the T data, we can see it's a 8-bit signal, so we can make another constant, and we can configure it to be 8 bytes or 8 bits long. And once that is done, we can connect it to the T data. The value is the same. It is also only 1, because we only want to do a FFT, a forward FFT, and all the other things do not change, and we can leave it as such. So yeah. So once that is done, our implementation is complete. So you can see the whole hierarchy here. So the processing system connected to the EXI interconnect, which is configuring the DMA through the EXI light. How we can see is by this EXI light that is coming, and the EXI DMA is using these two ports which are going out via the smart interconnect to the HP ports. So one more thing that we need to do is just to rename some of these IPs, just to make it a little bit more cleaner. So we can rename the DMA IP. We can just click on it once and it should give you the block properties, or you can just do right click and here you see via control E, or you can access the block properties here. So I have named it FFT_DMA, and let us name this IP as well to something a little bit more easier and more tidier. So now I am just changing this to FFT_S just to show that this is a streaming IP. It is taking streaming inputs and it's giving a streaming output. So I'm just naming it to be FFT_S. So the hierarchy name is FFT_block, the DMA name is FFT_DMA, and the streaming IP is FFT_S. In the address editor, we will see that we have the EXI light port shown, because it would be mapped on your processing system in your memory somewhere. The DMA also gets connected because it is the DMA data transfer is also shown here because it is connected to the HP ports, but there is no streaming IP present because we cannot directly we only see things which are directly connected to the memory itself. So basically anything which is not connected to the memory, so in this case we are only connecting the streaming IP via the DMA. It is not connected to the processing system directly via some interconnects and stuff. So these type of IPs are not shown here. We will also see these type of IP do not show up in the Pynq workflow as well. You will be using only the DMA itself to send and receive the data to and from the IP. So now once this is done, what we can do is just create an HDL wrapper, and it should take some time, and once the HDL wrapper is created, we can start by generating the bits. So let's just validate it once before we the validation is also done when we created the wrapper itself. So I'm just rerunning the validation to see if there are any errors. So there are no critical errors, and we can now generate the bit stream itself. So since it will take some time, I will just pause for right now, and whenever it comes back we will start from there. Okay, so the implementation is now done. So let's see how the Pynq workflow changes from now on. So we will export first of all our hardware similar to the SDK, and we will also include the bitstream for now. Rather than keeping it local to the project, what I will do is I will just keep it somewhere which is easier to spot. So we will keep it in bit streams for now, and yeah, so as you can see, it will copy our sysdef file and rename it to FFT8 wrapper.hdf. So this HDF file will be used in our Pynq workflow, and we will see how to deal with that. So now we will go to a specific folder in IP, the tutorials, and the bitstream. So we have created FFT_8 hardware handler file. So let me just remove these two files for now. So you can open it via a zip extractor. I'm using ARC here. So this is how your hard HDF file will look like, and we will require two files from it. One would be the hardware handoff file. In this case it is FFT_8.hardware handoff HWH, and we will require the bit file or the bit stream that is used to program your FPGA. So the bit stream would have the suffix of _wrapper, so we just need to remove that, and we can rename it to FFT_8.bit. So now these two files will be required to run our Pynq workflow. So we will just copy it to the Pynq port. So I am just copying them to the Pynq port here, and now we can log into our Pynq port and we can try to run the code itself. So here, let's see. So we will go to the port's IP. And we have copied it inside tutorials FFT_8, and you can see the same directory structure. We have a IPYNQ file, we have the 8-bit the bit stream file, and the hardware handoff file. Let us look how we can use this to create the similar to control the IP and see how it works. So yeah, so basically the first thing we need to do is to somehow program our FPGA with the specific bit stream that we have, and for that we will be using the overlay function. So the overlay, once we have imported it from Pynq, would program your FPGA board with the specific bit file that you supplied. So in this case it is FFT_8.bit, and it will also generate an overlay which you can use to see how the bit stream is what specific things that specific bit stream provides. So the overlay will provide you the overlay class will provide you object which will give you the idea about the IP. So in that case, you can see here it will tell you about the IP blocks, the hierarchy, any interrupts that you have connected, what type of GPIO outputs are there any memories connected. So in this case the DDR memory is shown here, and also basically it will show you what type of IP are present. So for example, if you remember, anything which is shown in the address block will be also shown in the IP blocks here. So the FFT_block and FFT_DMA, if you remember, FFT_block is our hierarchy, and inside that we have the FFT_DMA. So one reason why I wanted to rename it was to give it a better name so we can find it in the multiple IP blocks if we have them. So other than that, you can also see the hierarchies are listed here. The only hierarchy is FFT_block. And the interesting thing about Pynq is whenever it finds something which are commonly used, for example the DMA IP, which is very commonly used, so it has some functions which automatically connect to those IPs, and if it is not able to find it, it will connect it to the default IP, which gives you the access to the memory mapped input output. So you can write and read to the registers and stuff. Here in the DMA, since DMA is a little bit complex, it automatically provided you with some functions which are pre-written, and you can also write your own IP drivers and connect them to specific HLS IPs or specific IPs in your hierarchies or in your design. So once that is done, now I need to access this FFT DMA to somehow send and receive data, right? So how this access work is, we use the dot as an accessor. So OL or the overlay dot the hierarchy dot the IP that I want to use. So the dot is used as an accessor, and I can have an instance of this FFT underscore DMA as my data channel. So how does this data channel looks like? So it is again a class basically, which gives you some functions to deal with simple DMA engines. And as you can see, there are two attributes, one for reading and one for writing, and there is these attributes are receive channel and send channel, and there is another attribute which tells you the maximum size of transfer that you can do on this DMA. So this is determined by your buffer length register that we set to max. So once this is done, we have seen how this data channel looks like. Let us start with creation of the golden output and some data for the 8.FFT. So I am using NumPy and matplotlib because we are using Python, and this is a very quick way to generate some data. So as you can see, I am just creating 8 samples of 8. I am creating a line, and I am creating this type of data, which is 0, 1, 2, 2, 1, 0, 1, 2. So once this is done, I can just using the absolute function, because I am defining the data type to be np.csingle. This means this creates a complex number of 64 bits, which has 32-bit precision in real and 32-bit precision in imaginary part. So it's a single precision floating point real and a single precision floating point imaginary. So once that is done, I can go ahead and do a CPU implementation. So the data has been created. I have plotted out the data of how it looks like, and now what we are doing is we are trying to figure out a golden output. For that also I am using a very simple thing. I am using the internal FFT functions of NumPy and using np.fft.fft and providing it with the specific data. As you can see, it will take a very small amount of time. It was taking like 423 microseconds, and if I run it multiple times, and sometimes the time function jumps because we are not really doing it on bare metal. There are multiple things involved. So yeah, but most of the outputs are in microseconds, while leaving some of them out. So the data is set to golden output, and we can see how the data looks like once we plot it. So I am plotting the absolute value of the golden output because the golden output is very complex value. So as you can see, this is how the golden output plotted looks like. And let us start with the PL implementation now. So you can see the CPU implementation is very small now, because we are using the internal functions on NumPy, and functions from NumPy and other libraries are highly optimized because they are open source, and people use it on a very regular basis. They use all the features of the CPUs, like vectorization and SIMD type of instructions, and try to optimize it as much as possible. That's why we are getting a very low score, like 385 microseconds and stuff. Now for the PL implementation, if we remember, the DMA requires a single big buffer from which it can copy and paste to. So we will use the allocate function, and the allocate will allocate 2 buffers. In this case it would be as you can see, it's a size 8 buffer for the input and size 8 buffer for the output. And we need to remember that we are using C single because our FFT library, or the FFT IP that we have, uses 64-bit inputs and outputs, which are 32-bit real and 32-bit imaginary. so we are using the C single. If these are not kept properly, the output sent and received from the IP would not be proper. So after this, we will create the send and receive channel. So the data, we are using the data channel, which is the DMA IP, and we are just storing the references to send and receive channel. After that, I'm just copying my data to the input buffer, and just to see how the input buffer looks like, it is just similar to a numpy array, but it is said to be a PYNQ buffer. So this is numpy ND array, which is physically contiguous memory, and so the DMAs can use it. The thing with PYNQ buffer or the allocate function is, it will create a buffer and give you a buffer which will also have its physical address attached to it. So if I want to see the address of this buffer, I can do input buffer.device address to see the address. And the idea is the DMAs need a lot of things to send the data. So the DMA requires a physical address from which it should start. The DMA requires the length of the whole buffer that it needs to send or receive. So these two parameters are kind of internal to this input buffer, and when we use this transfer function here, so when we use this transfer function, send channel dot transfer input buffer and receive channel dot transfer output buffer, so the transfer function sees the input buffer, it will get the physical address from the input buffer, it will also get the size of the buffer, and it will configure the DMA using these functions. So since we do not need to go on the register level for this case, because we have the device driver for the DMA, it makes it a little bit easier to program the DMA and send and receive data from the DMA. We will wait for the send channel until it is done sending the data, and we will wait for the receive channel until it is done receiving the data. And once that is done, we can continue with our program itself. We can do asynchronous waits as well, but we can see it in a later video. So for this, we will just plot the output buffer once. So you can see here the graph output for the PS implementation, the CPU implementation or the PS implementation is very similar to the PL implementation as well. We are again plotting the absolute itself, and now we will just look into what's the difference between the golden output, which was on the PS, and the output found on the PL implementation. As you can see, in the PL there is some difference between PS and PL implementation, but the difference is in 10 to the power minus 8. So the maximum difference that we are getting is, you can see the scale, 4 into 10 to the power minus 8, and the minimum distance is basically the error is in the range of -4 to +4 into 10 to the power minus 8. So this is because we are using in the CPU implementation, the FFT uses complex 128 bits, which means double precision for PL and double precision for the imaginary part, and this will give you a higher precision data as an output, while in the PL implementation we are limited to single precision in real and single precision in imaginary, which is 64-bit complex numbers. So the precision here drops, and that what causes the small differences in the PS and the PL implementation. So one thing that we note is, basically if we see the PS implementation or the CPU implementation, it is using significantly more bits. It is giving you higher precision, and it is also computing the data in relatively lower time. So it is doing the computation in 253 microseconds or 400 microseconds or 240. Sometimes it jumps to milliseconds, but most of the times it is doing the computation in microseconds. While in the case of PL implementation, we can see we can see the time it takes to run our implementation takes considerably long time, which is in milliseconds. So here in the PS we are doing higher precision computations in microseconds, and in PL we are doing it in milliseconds. So sometimes the code, for example in the CPU implementation, if we have highly optimized codes, we can also outpace the PL implementation if it is not properly optimized. One of the cases is that we are sending the time required to do the cache flushes and send data from PS to the PL using from the memory, from the HV ports, requires considerably more time for such small types of computations which are only 8 bits. So the PS can quickly compute it until the data is sent and then compute it and sent back. So once this is completed, we can go towards the other implementation where it is for 1024 and see how it is different from the 8-bit implementation.
Okay, so we will now look into how we will do the implementation for FFT 1024 point, and I have already created the block diagram in the similar manner to FFT 8 point, and we will see what are the changes that we have done. So as you can see, we have a similar block diagram where we have the processing system, the interconnects, the smart connect and the AXI interconnect, and we have also made a hierarchy which is same as FFT underscore block, and inside the hierarchy we see our Fourier transform IP, the DMA IP, and and we have made the MAXI memory map to stream and stream to memory map ports as external. The AXI light port is also external. Now, so let's see what changes have we done in the FFT DMA. So the scatter gather engine is already disabled. The buffer length register is set to maximum, which is 26. The read and the read channel is set to 64, and the stream data width, the memory map width is set to 64, and the stream data width is also set to 64. We have also increased the size of the burst size to be 256, and we will also increase the max burst size for the write channel to be 256, because we would be sending 1024 values and we want to do it in minimum number of bursts, right? So that is all the changes in the FFT or the DMA IP for the FFT underscore DMA. And in the 1024.FFT, let's see what else we need to add or remove. So the first change would be the transform length. We want the FFT to be 1024 points, so the transform length is changed from 8 to 1024. In the implementation, this is the same as floating point. The reset signal is still needed, and the output ordering is in natural order. Other than that, there are no major changes in the FFT IP. Another change that we need to do would be the size of the T data. The T data now is of 16 bits rather than 8 bits. So rather than sending it only 1 bit value or a 8 bit value, I'm sending it a 16 bit value, and the value still remains 1. Here as well, the T valid signal remains the same because it's a 1 bit value, and it is also set to 1. Other than that, all the connections to and from the IP remain same. The clocks and the reset signals are connected with the FFT IP and the DMA IP, and similarly the reset is also connected to FFT and the DMA. So now we can generate the bit stream, and I will just copy the files, the hardware handoff file and the bitstream file in the respective folder. Okay, so now I have copied my bitstream file and the hardware handle file in the Pynq board, and now let's see what do we need to do for the 1024 point FFT. So again, here I am just importing the overlay function or the overlay class, creating an object of the overlay using the FFT underscore 1024 bit stream that we have, and let's see how the overlay looks like. So here you can see the overlay again contains a DMA block inside the hierarchy of FFT underscore block and FFT, and named as FFT underscore DMA. So I'm just using the dot accessor to get the DMA IP, object of the DMA IP to interact with data in and data out. And now we can start with the data creation and passing the data to the IP and the PS and PL implementation. So in the data creation, I'm again using NumPy, matplotlib, and I'm using import. I'm importing random just to create some random input. So for currently, I am using random to get values from 10 to 50 for the frequencies. So there are 3 frequencies from 10 to 50, and then there are 3 amplitudes which can be from 1 to 1000. And basically I am trying to generate a sine wave of 3 sine waves of different amplitudes and frequencies. So amplitude 1, omega 1 would be the first sine wave, amplitude 2, omega 2 would be the second, and amplitude 3, omega 3 would be the third sine wave, and adding them together gives me the signal that I want to create the FFT of. So just here I am just I have just taken some random values for frequencies and the amplitudes, and now I am just creating the data, and let's just plot the data and see how the data looks like. So as you can see, the data is now plotted, and we have the values from minus 1500 to 1500, and this is kind of the addition of the 3 sine waves that we have. Now let's start with the PS implementation or the CPU implementation, and we will time it how much time it takes. So as you can see, when I'm running the FFT, I am getting around some milliseconds of time to run the FFT for the 1024 points. In the previous cases, I was getting the output to be in microseconds because the size of the FFT was small. Here you can see this varies from 1 to 8, or sometimes it gets to microseconds, but in very rare cases, but it almost always stays more than 1 millisecond or like 5 or 3 milliseconds. So once I have generated the golden output, what I will do is I will just try to plot this and see how my FFT is looking out. So here you can see that the FFT has 3 peaks for the 3 sine waves, and the amplitude of these peaks are different because the amplitude of the sine waves were different, or I would rather say they were random. So there are 3 random peaks of random amplitude. So once we are done with this, we can go ahead and start with the PL implementation. And in the PL implementation, I am again going to use the allocate function to allocate the contiguous buffer that we have talked about. So these are Pynq buffers which are contiguous, so the DMA can use it. And I am using np.c single because the values that we want to send to the FFT should be 32-bit real and 32-bit imaginary, which makes it a 64-bit complex number. So a C single represent that data type. So I will then get the send and receive channel from the DMA, and I will copy the data to the input buffer. Here I am just printing out the input buffer to see how the input buffer looks like. And now we will start with the PL implementation. So the thing I need to do is I need to transfer the data to the transfer data from DMA to the streaming FFT IP, and I will receive the data back from the DMA of which is the output of the streaming FFT IP. So I'm sending the input buffer via the send channel, and I'm receiving the data in the output buffer via the receive channel. For this, I will wait for the send and receive channel. Once they are done, I will end end the whole block, and this will time the whole send and receive cycle for the FFT itself. So here you can see it is still coming out to be between 1 and sometime it jumps out to 8 milliseconds or stuff like that, but it is close to whatever implementation we have done in the CPU itself. So here we can also plot the output for the PS and the PL, and you can see we are getting the same result as the PS. So there are 3 peaks here and there are 3 peaks here of kind of similar amplitude. So just to get a match out of it, that the amplitudes are same and the PS and the PL implementation are matching, what I have done is now I have plotted the PS and the PL implementation on the same graph, and let's see what's the outputs looks like. So as you can see, there is only one graph that is showing up, because the other graph is kind of overlapped. The other graph is kind of hidden behind the graph in the front. So one is plotted in blue, other is in orange. So the second graph is only visible. So we can see that the PS and the PL implementation, the output of the PS and the PL implementation are very close to each other, and we can see that by taking the difference from absolute difference of the PS and the PL implementation. So here I am just plotting the absolute of the golden output and the output buffer. So if I plot this, we will see that we are in the order of 10 to the power. We are in the order of -2, which is 10 to the power -2. So the maximum error that I am getting is 3.5 into 10 to the power -2. So once this is done, we can see that the PS implementation is still kind of holding, kind of still working out to be pretty much okay for 1024.FFT, because the library for the FFT library uses the SIMD and the vectorization operations of your CPU very efficiently, and still the PL implementation is kind of neck to neck to the CPU implementation. One more thing that I should remind you of, that the PS implementation is doing this in complex 128 bits, where the PL implementation is doing all the operations in complex 64 bits. So still we are kind of neck to neck to the PS implementation. We have seen how the code basically looks like for the PYNQ workflow here for the 8.FFT and the 1024.FFT. But one of the advantages of this PYNQ workflow is that we can use Jupyter or Jupyter notebooks and the whole Python workflow to get us more presentable and interactive codes that will kind of give you a front end to basically work with your whole IPs and see how your IP behaves on different inputs and outputs. For example, we have something called Voila basically, which re-renders your whole IPYNV files and only shows you how the different graphs and how different comments that you have written, and only shows you the output of them. So it will take some time to run all the cell blocks because it renders the whole. It will take all the individual cell blocks and it will render them, or it will run them and then render a web page out of it. So as you can see, this once the Voila has generated or run all the code blocks, it has rendered you a web page that you can show whatever findings that you get for your individual IPs and present it without showing any code that you might need to explain and stuff like that. So basically here you can see the plot for the data creation. Here the data is created, after that the CPU implementation, then the time it took for the CPU implementation, and then I have plotted the PS implementation, which is plotted here. After that the PL implementation was done. I have taken the time of the PL implementation, which is 1.58 milliseconds. Here it is 1.18 milliseconds in the PS implementation, and then I simply plotted the PS and the PL on the same plot, and they came out pretty close. And here you can see the errors for the difference between the PSPL implementation, which is still in the order of 10-2 or 10 to the power -2, but the error is a little less from the previous case. Now this is just the starting point of what Viola or Jupyter Notebook can do for your code. Another example that I can give you is this another IPYNV file that I have created to make my code a little bit more interactive with the inputs and outputs. So let's just first start with the demonstration, and we will come back to how the code looks like. So again, it will compile the whole all the cell blocks, different cell blocks, and once it is done with executing all the cell blocks, it will give you a rendered page for the IPYNV file that you have. So in this case, what I have done is I have created 3 sine waves, just like the previous demo. But instead of giving them some random value, I have given the user the opportunity to use sliders to set individual components of the individual sine wave. So for example, I can change the amplitude. So currently the max amplitude is 300. I can change the amplitude of the first wave, and we can see once it loads the so as you can see here, once it loads, I have increased the whole amplitude to 200, and now the maximum value goes till 400. Then again, let's change the frequency for it. Let's change the frequency of the second wave, and you can see my output waveform is now changing to whatever I have set the frequencies to. So for example, now let's change the first frequencies as well. So here I'm changing the frequency, and now my output graph is also changing. So let's set it to something random. Here I am setting it like this. So now this is the waveform that we have generated for our as our input to our FFT function. So now on the second part of it, what I'm doing is I'm creating a FFT functions, and I have the option to choose either the PS implementation or the PL implementation, and then I need to press this button to start rendering the PS or the PL implementation. So let's just print the PS implementation for now. So once that is done, as you can see, now I get the PS implementation and I get the FFT to be something like this, with 3 different amplitudes and 3 different frequencies. Let's see the PL implementation and remove the PS implementation. It renders to be the same. There are no changes because we have already seen that they overlap, so there are no differences here. But if I change something here, let's say frequency, I change it to 108 and press run interact, as you can see, the graph changes here, and the above graph also changes because these 2 sliders are just the same. They are rendered in 2 places because of the interact functions that we are using. So Now if I want to, I can also do PS and PL implementation on the same graph, and since we are doing it on the same graph, they are kind of overlap and only one of the graphs are showing, but the implementation is shown. So as you can see, this gives you a lot more flexibility of how to send your inputs, or gives you the ability to play with your inputs and show how your output changes with different inputs. So let's see how the code of this is different from the code we have written for the 1024 IP PYNQ, or the basic code that we have written here. So let's just open it. So basically, as you can see, I am using the overlay and the allocate function as the same, and the only new thing that I am importing is the IPy widgets, which will give me the ability to create these widgets that we are seeing here. So all these sliders, all these checkboxes that we see are the widgets that we want to use. And then I have also taken numpy and matplotlib just to get some input values, and again creating an overlay just as before, getting the DMA IP to send and receive the data. These functions remain the same. And now the part which creates the sliders is here. So I am using widget.float slider. It will create a floating point slider. So I can, if I set the step to something 0.05, it will take those value and it will return a float value from the slider. So this slider, when I slide this, returns the value written here to the specific function that we want to interact with. So here I am just giving it the description, that is it is a frequency. Then I have created 6 sliders, 3 for amplitude and 3 for frequencies, and all of them are float sliders. This kind of creates your sliders for this type of implementation, and we will see what is needed to be done. So now I will create the data. First of all, creating the data would require 3 amplitudes and 3 frequencies. So I'm just creating the same sine wave and returning the data. So this is just a data creation function. After that, what I'm doing is I'm also making a graph function which will graph what was the input. So as you can see, I'm plotting the input function basically. So just sometime it will automatically come out to be, yeah. So as you can see, here is the input function that we have, or the data that we have that we need to plot. So this plot is present here. So I need to plot this graph. So for that, I am just getting the data. I am getting a subplot which is similar to plt.plot. It's just plotting this, and I am showing the figure. And now I need to make it this graph interactable, that the values of this plot changes when I change the individual sliders. So for that, I will be using a interact function of the widgets. Interact function basically takes an input of one of the functions that you want to make interactable, and then it will take the individual values that you want to send to the graph itself. So as you can see here, I am sending the plot graph values of values A1. So the arguments here will are present here. So basically A1, I am mapping it to A1, which is the float slider, and it will automatically get the values of internal values of the float slider. So in the internal value of the float slider would be the wherever I have stopped the slider, whatever value is at that point. For example here, value of the A1 slider is 153. It will take that value and give it as an input to the plot graph function. Similarly for A2, it will take the value from A2, and similarly for A3, F1, F2 and F3. So widget.interact will automatically change the value whenever, automatically re-render the whole function whenever I change any slider value. So once the slider is set, it will automatically re-render the whole function, or rerun the whole function and re-render the outputs. So once this is done, I have plotted my data. I have plotted my data how it looks like, and I have the ability to change the values individually. Now I want to plot the FFT as well, and I want to also be able to check which implementation I want to show. So do I want to show the PS implementation or the PL implementation? For that I have created two widgets, one for PS, one for PL, and both of them are checkboxes. So as you see here, these are the checkboxes, and basically the default value for them is true. The description just says what type of implementation they are, or what they represent basically, and this is a string that you can write on your own. So for the plot FFT, I'm taking again 3 inputs for amplitude, 3 for frequencies. I am creating the data. The function to create the data will basically give you the addition of the 3 sine waves that are created. I am making a plot, and now I am using the PS or the PL as a boolean value. If the PS is true, I will plot the PS implementation, so the np.fft.fft.data, and the absolute value of it I will plot on the graph. And if the PL implementation is true, I will do the PL part of it. So taking the input buffer, setting it, output buffer, allocating the output buffer, after that copying the value to input buffer, sending the data on the send channel, whatever is written in the input buffer, and receiving the data in the output buffer through the receive channel. And then we will wait for the PL implementation to end, and after that I am just plotting out the output buffer, similar I am doing for the PS as well, and then I am just showing whatever the figure is plotted here. So now this function is needed to be interactive, but since this function is a little bit slow, I do not want it to be re-rendered every time the values are kind of changed. So I do not want, whenever I change this, all these values, this will take a little bit more time to regenerate or run the whole function, because we need to do FFTs which are kind of a little bit on the slower side, right? Rather than just plotting it on the graph, I need to first compute something which is compute intensive and then plot the graph. So rather than doing that, it might be better to have a button which will tell that the values are set, and now we need to rerun the whole function and recompile the output for it. So here you can see this button is run interact button is added by the interact _ manual. So rather than interacting whenever the sliders are changed, I can use the interact manual function, which will generate the output once I click this run interact button here. So again, it is similar to interact. It takes a function, then after the function I need to give it all the arguments for the function, and the arguments can be your sliders, your checkboxes, or whatever widgets that you have. I can change individual values. I can change individual values to floating point, and basically there would be no changes, no differences from keeping it as a float slider or a int slider or something like that. So whenever you write something like a tuple, let's say 0, 1 and 2, it will keep it as a list, or it will if you give it a list, it will keep it as a slider, and you can mix and match with different data types to see how it changes. But it can take any of the values, and it will kind of try to get the values inside the basically the internal values which are needed by your function. So the FFT function needs only the floating point values. So when I give it the slider function or the float slider, it will take the values which is represented by the slider. So just to go on that again, for A1 the slider value is 153, for A2 it will be 123. So for here the A1 that would be passed to the function which is internal create data would be 123 and 152 and stuff like that, not the sliders itself. So that kind of concludes most part of our 8-point FFT and the 1024-point FFT, and we have also seen how Viola or Voila can give you some interesting ways to give inputs to your IPs and get the outputs and present them in a more interactive manner. And that's all. Thank you.